Okay, so what we have here is 4 different types of logic, different families. They're all exactly the same part, except for one is a little bit different. 3 of them are 74XX, where XX is the logic family, the technology, 04, which means there are 6 inverters in each one. And what we're doing is we're putting a signal into each one of them that's identical, and we're looking at the output. And the signal we're putting in just happens to be a 1 kilohertz, 0 to 5 volt square wave. But we have the ability to add noise, and what we're going to look at is how the noise affects the output of these 4 devices. We're going to start by looking at 3 devices, the 74XX04s. If you look on the breadboard, on the far left is a 74LS04. That's a bipolar part from 30 or 40 years ago. The next one is a 74HCT part. That's a CMOS part, but it's designed to work with the bipolar, the LS parts. So it has signal levels that are guaranteed to work with the LS part. And then the third part there is a 74HC04. That's a pure CMOS part, and that has levels that are designed to work with other CMOS parts, and that tends to have the widest range of levels. So now let's take a look at what the signals look like. What we have here is our function generator. Right now our function generator is looking at the noise source. The noise source is just an 8-something kilohertz sine wave. Right now it's turned way down, so it's effectively not visible in the input signal. And it goes through a voltage divider, so you'll see fairly large values on that of volts, but they get divided down. We'll actually look at the input signal to the 4 inverters and see what the magnitude of the noise is. So our input signal is at the top in yellow. It's just a 1 kilohertz, 0 to 5 volt square wave. The blue signal just under it is the output of the 74LS02. It's inverted because this is a hex inverter, and what's interesting to note is that the output goes from 0 up to something less than 5 volts. It's hard to tell here, but it looks like it's just a little under 4 volts. And that's typical of the bipolar technology. The bipolar technology's output doesn't go all the way up to 5 volts. The next signal down, the purple one, is our 74HCT, which is our CMOS technology that's designed to work with the LS technology. And you can see that goes from 0 to 5 volts. And then finally at the bottom is the pure CMOS, the 74HC04. Now, there's no noise being added, and all 3 of them work just fine. What I'm going to do now is start adding noise. I'm going to start by adding 1 volt of noise, peak to peak. Now remember, when I say 1 volt, I mean the output of the function generator. You can see that the actual noise on the input signal is pretty small. It's hard to tell, but it's maybe half a volt or so, or a quarter volt. And you can see that all 3 devices work fine. And that, of course, is the beauty of the digital world, is that the devices only have to tell us the input is a 0 or a 1, and a little bit of noise on a 0 or a little bit of noise on a 1 really doesn't make that determination difficult. Now, as we start to increase the amount of noise on the input, so now we've got, it looks to me like maybe a little over 1.5 volts of noise, and once again you can see that all 3 outputs look pretty good. I start adding a little bit more noise. Now I've got quite a bit of noise there. I would say that noise is on the order of 2 volts peak to peak maybe. And once again, that doesn't affect our output. So we can have a fair amount of noise in our digital signals, and we can still discern whether they're high or low. Let's just add a little more noise, a little more noise. We're doing pretty good. Uh-oh. Now we're getting to a point, maybe 3 volts peak to peak noise, or 2.5 I would say, where we can see something happening in the LS, the bipolar device. And indeed, as we talked about, the bipolar devices have lower noise immunity. Okay, so now we're going to add a little more noise. And you can see that the TTL signal, the LS part, really no longer knows whether the input, particularly when the input is low with noise on it, is a high or low. It should be always high when the input is low, but it's actually going low. It's inverting, thinking the input is a high signal. And that's because we've now reached the noise margin threshold of the LS device. But notice the two CMOS devices, even the HCT, still are working fine. I can add a little more noise. So let's see. Okay, so now I've finally reached a point where the HCT device, the device that has logic levels designed to work with the bipolar, no longer can tell that a low signal is low. Every so often it thinks the low signal is high. Notice that the noise immunity for the high signal with noise is much better than the signal input for low. You just got to remember, these are inverted. So what these are looking at is this signal, and they can't tell that it's a low. This signal says, I know that's a high, and I'm going to be low. Let's add a little more noise. At this level of noise, which is quite large, it's almost half the amplitude of our signal, neither the LS part or the HCT part is functional. But our HC part can still tell that this is a high signal, even with quite a large amount of noise on it, and this is a low signal. And if I add a little bit more, we finally reach a point where even the HC can't tell. When I reach the point where the noise goes above half of the signal size, or up or half down, it's not going to work. And let me just add the noise in a little smaller increments. So we can see that right around there, even the HC can no longer tell that this signal is always high. Notice, by the way, that the HC error occurs when the input signal is high, whereas the LS and HCT when it's low, and that's just a function of how the logic levels are defined. But if we go back, here we have a signal with a huge amount of noise, and yet our logic can tell that this input is high and inverts it, and this input is low. And that is really the thing we like about digital logic, is it's very immune to noise. Now we're going to make a change. We're going to look at yet another type of logic device. This is a 74HC14. Now 74HC14 is also inverter, but it has a Schmidt trigger input, and the Schmidt trigger input requires the input to go higher than half of the total voltage to switch in one direction, and then go lower than half the total voltage go in the other. It has asymmetrical trigger points, and that's going to give us even better noise immunity. So what I'm going to do is, first of all, I'm going to turn off the TTL, the LS part. I'm going to back off the noise a bit, go back to no noise, and I'm going to move the purple, which was connected to the HCT, to the Schmidt trigger output. Now, the 74HC04, which is the bottom trace, and the purple 74HC14 have exactly the same pinout. They're hex inverters. The difference is the purple one has this asymmetrical switching, and let's go ahead and start adding noise and see how that affects everything. Start out with the same noise we had before. We get a little bit of noise. Let's go up to the point where the HC device stopped working. All right, so we're right about there. I need to change my trigger to the channel that's working well, and that in that case is channel 3. And you can see that we are now at a point where the noise is so large that the HC device can't tell what's a high anymore, but the Schmidt trigger device is still working properly. And in fact, I can actually make the noise larger than half the signal, and the Schmidt trigger device continues to work properly. Let me just single step that. So our input signal is actually going lower than when it's high, then the input signal is going higher than it's low. So we are overlapping, but because the thresholds are different going up and going down, Schmidt trigger device can still discern. Now, Schmidt trigger isn't a different technology. These are both HC CMOS devices. It's a different circuit design. We normally would use the Schmidt trigger device when we have a slow moving input waveform to stop it from double triggering. We don't normally use it for regular use because it tends to be slower, and we care about speed in digital circuits. So I think that's a pretty good demonstration of why we like digital and why the HC technology is so nice. Now the next demonstration is we'll show you what happens when your noise is so large, even the Schmidt trigger or the HC devices are not adequate to discern the signal among the noise.